the last lecture, I had taken an actual data from an X-ray diffractometer to analyze the crystal structure of a material. And this data, I have just recopied this data here. So, this was the 2 theta values, the scattering angle values were taken from the X-ray diffractometer data, and from there on we analyzed the structure to be that of a face centered cubic material. And the peaks at which these 2 theta values are occurring, we also indexed those peaks and determined what should be the HKL indices for those peaks. Now, suppose we want to determine using this data, I want to find out what is the lattice parameter for this material. Now, since this is a cubic structure, there is only one lattice parameter, and essentially we will call that as A, the edge length of the cube. Now, in order to find the lattice parameter, we can go back to the Bragg equation, lambda equals 2d sin theta. From there we get the interplanar spacing as for lambda d is equal to lambda upon 2 sin theta. Now, this we will get a number of d values from each of the peaks, and obviously the first peak which we have indexed as 111 would be the interplanar spacing for the 111 plane. Second peak where we have indexed the peak as 200, the interplanar spacing would be for 200 plane, and so on. So, there are 6 peaks, so we can get 6 different d values. Once one has found out the d values, then since this is a cubic structure, the lattice parameter can now simply be related as, or let me write in the usual way, that the d value itself is equal to the lattice parameter A divided by h square plus k square plus L square to power half. So, I have these 2 equations, I get the d values from here, from the first equation, and then we come to the second equation, and from there one can find the lattice parameter as simply A equals d times h square plus k square plus L square to power half. So, now again from each of the peaks I will get lattice parameter value, and of course, they must all give me the same lattice parameter values, but of course, since this is an experimental data, we would get some differences in each of the A values than one gets. So, now suppose now I want to find out an accurate value as accurate as possible. What could be a good idea? One possibility could be that I can take all the A values I get. We do this in so many experiments. When we get several values for the same measurement, we take an average. But here, taking an average of all the A values, all the lattice parameter values may not be such a good idea. And let us see why that is not such a good idea, and then let us see how we can get a better value for the lattice parameter. So, what we are going to look at is an error propagation. That how does error propagate starting from the X-ray diffractometer data where we are measuring theta values, and then we are computing the A value. So, if there is an error in theta for a given peak, the measurement of angle theta, this will clearly impact the d value. So, there would be an error in the interplanar spacing for that specific HKL plane, and then since A is now related to the d value, this will produce an error in the lattice parameter. So, this is how the error is propagating, first from delta theta, then to delta d, and then to delta A, and then to A. So, let us write this in a different way. Let us try to write a fractional error. in fractional error in lattice parameter A could be written as delta A divided by A. Now, this would be equal to, if I look at this equation here, this one, delta A is could be written as delta D h square plus k square plus L square to power half. I am simply differentiated it, divided by A, and A could be written as D divided by h square plus k square plus L square to power half. So, this is for a specific peak. Now, these terms will get cancelled. So, what I get is delta D upon D. Now, let us look at delta D. Delta D can be written as, let us consider this equation and differentiate this. So, this would be delta lambda upon 2 sin theta divided by D, which can be written as lambda upon 2 sin theta. Therefore, delta A upon A, and differentiating the numerator, I will get lambda upon 2 minus cos theta upon sin square theta. I am differentiating 1 upon sin theta times delta theta divided by lambda upon 2 sin theta. Clearly, many terms will cancel out, lambda will go, 2 will go, sin theta and 1 of the sin square theta. So, only sin theta will be left, and what I have is now minus cos theta upon sin theta delta theta, which can also be written as minus cot theta delta theta. Now, let us examine what we have obtained. What happens, let us say, as theta decreases. As theta decreases, clearly cot theta value will increase, which implies, and if I just look at the absolute value of delta A upon A, this will increase. So, here as theta is decreasing, the error in calculation of lattice parameter is increasing, and it is the reverse. As theta increases, magnitude of cot theta decreases, implies that the absolute value of the error in lattice parameter will go down, and clearly as theta tends to pi by 2, as theta tends to pi by 2, cot theta tends to 0, delta A upon A would also tend to 0. So, from this you can see that there is a systematic error in the calculation of the lattice parameter as theta changes. Lower values of theta will give us larger error in the lattice parameter, higher values of theta will give us smaller error in the lattice parameter, and at theta is equal to pi by 2, the error should go to 0. So, this is how the error propagation is taking place. So, obviously, we would like to have a peak at an incident angle of 90 degrees. Well, one cannot get a peak at 90 degrees. What one has is a data where there are specific peaks at specific angles. So, one conclusion from here is simply that peaks at higher Bragg angle will give better values of lattice parameter. So, one is simply that take the highest angle peak and calculate a lattice parameter from there, but then that's you only have one single value. Can we still use all of the lattice parameter values that we have calculated from the individual peaks and get a good value for the lattice parameter? Well, there is a way out. There are some functions which can be used for extrapolating the value of the lattice parameter to theta equals 90 degrees or theta equals pi by 2. So, what one does in that is there are a couple of functions that I am going to point out here. We are not going to go into the derivation for these functions. One is the Bradley J function, where this function is quite a simple function. It is simply cos square theta. So, what one would do is make a plot cos square theta on the x axis and the lattice parameter values calculated at specific angles of theta on the y axis, and plot the data in this fashion for specific theta values. One is plotting A versus cos square theta. Now, here we fit a straight line. One can use the least square method for doing this fitting, and suppose this is the best fit line. It will intersect the vertical axis at this point where cos square theta is 0, which means that if cos square theta is 0, which means theta here is pi by 2. So, by fitting the line and extrapolating it to cos square theta equal to 0, which means extrapolating it to theta equals pi by 2, we get a lattice parameter value, let us call that as let us say A0, which could be considered as the best value from the data that we have using this Bradley J function as the extrapolation function. Now, same thing one can do with the second function. Let me first introduce that function, which is called as the Nelson-Rayleigh function. Now, Nelson-Rayleigh function is also a fairly simple function, cos square theta upon sin theta plus cos theta divided by simply theta. Now, here also we do the same thing with the data. Here on the x axis one puts the Nelson-Rayleigh function, out here is the lattice parameter, and then plot A versus the Nelson-Rayleigh function. Again, do a best fit line through this set of points using least squares and obtain the value of A0, which we will consider as sometimes this value is also called as a precision value or precision determination of lattice parameter. Generally, the Nelson-Rayleigh function, extrapolation function, is considered as a better function to use than the cos square theta function. So, one can quite easily do this with the data that we have obtained from the X-ray diffractometer. Calculate, as I said, calculate the lattice parameter for each peak. After that, use one of these functions, plot the lattice parameter values and do a best fit line. And you could actually quite easily do it if you take a spreadsheet like Microsoft Excel, put the data there, plot it, use the trend line function to get your best fit line and get the intercept on the y axis to obtain the precision lattice parameter. So, what I will do is I leave this as a assignment for you to do, taking the data that I have presented here, find out using, let us say, the Nelson-Rayleigh function, the precision value of the lattice parameter. Another thing, the material that we have analyzed is actually an element in the periodic table. So, from the lattice parameter value, search which element it is in the periodic table by matching its crystal structure, which is face centered cubic, and matching the lattice parameter to determine which material it is from which we got the diffraction pattern. Now, just a few comments on what we have done is we have done indexing of a cubic crystal. How about it if I have to index non-cubic crystals? Let us say I take an example of a tetragonal system. Now, here the interplanar spacing is not as simple as in the case of the cubic crystal. Here the interplanar spacing d is given by this expression, h square plus k square divided by a square plus l square upon c square. Here essentially a equals b not equal to c, all the angles are orthogonal. Now, here if I start with the Bragg's law, I have got a diffraction data with me. So, starting with the Bragg's law, lambda equals 2d sin theta, I can write this as sin square theta equals lambda square upon 4 d square, which could be written as lambda square upon 4 a square h square plus k square plus lambda square upon 4 c square l square. So, here how does, I am not going to actually analyze data from here, but I will just give just a few comments on how one could go about doing it. One may again get a series of peaks at different Bragg angles, and now we have to kind of try to index them starting from the largest interplanar spacing planes all the way down the diffraction pattern. Well, one way one can think about it is that we look at groups of peaks. We look for, let us say, peaks which have indices of hk0. We do not know which ones are there, but let us say that I am only trying to figure out what those peaks are which have the indices hk0. Now, hk0 means that I can list down what are the indices in decreasing interplanar spacing. I can start with 100, h square plus k square is 1, 110, this is 2, 200, it is 4, 210, 5, and like that 220 is 8. Since L is 0, for these sin square theta would be proportional to h square plus k square. So, one can go in exactly the same way that we did with the cubic system, except that here we will have to look at which are the peaks which will conform to this proportionality between the sin square theta and h square plus k square. And on top of that, if it is a primitive one, then all of these planes will produce diffraction. But suppose it is BCT, body centered tetragonal, then clearly some peaks should be should not be visible like the 100 peak, because H plus K plus L should be even. 210 would not be there among these peaks, but all other peaks should be possible. In a similar way, one can now try to index peaks which have the indices 00L. So, here very clearly sin square theta would be proportional to L square. So, I can try to analyze 001, 002, 003 and so on, and here you have your L square value. So, 1, 4, 9 and try to figure out where those peaks are. When I am able to analyze, let us say, the peaks which are of the HK0 type, then I can get the lattice parameter A. Try to analyze 00L peak, this will give me the lattice parameter C, and then eventually I should also be able to index those peaks which are in general HKL, which would be the remaining peaks once we have done this. Now, this method is okay for working with crystals which have 2 lattice parameters to be determined, but anything higher, anything more in which we have to determine more than 2 parameters, and then angles are also not necessarily 90 degrees, these methods become impractical. And anyway, today most of the job gets done by computers, and they are able to figure out a lot of things, even space groups, etc., that what space group should be there from the diffraction patterns. And finally, before I conclude this lecture, what are the other applications? What we have seen here, we have seen determination of crystal structures, determination of lattice parameters, determination of crystal orientation and so on, but then there are other important applications like phase identification. If more than one phase is present, so more than basically one type of crystal structures are present, one should be able to identify those crystal structures, because then you will get peaks in which peaks will be mixed from multiple phases. Phase quantification, phase quantification means what is the volume percent of the phases that are present in the structure. This can be obtained, suppose I have a peak, this can be obtained by the intensity of the peak, and the intensity of the peak is calculated what is called as the integrated intensity, that is the area under the peak. We can determine crystallite size. I had very briefly mentioned this in an earlier lecture, and that is determined from the width of the peak. In fact, it is not just the crystallite size, it is also crystallite size and residual stresses and so on. There is a whole list of applications that are there using X-ray diffraction. So, X-ray diffraction is an extremely important tool for determining many aspects of the structure of materials. Thank you.